Good afternoon, Physics 20. I hope you guys are enjoying this lovely August day. So, what we're doing, well, by the time you guys watch this, it'll be like September, October or something. For me, it's August. All right. So, ladies and gentlemen, today what we're going to be doing is we are going to be looking at projectile motion. Like the last topic with your 2D vector problems, I'm going to be breaking this topic into two separate videos. So for the exact same reason, because we've got a couple of challenging different topics here in this. We're going to be looking at projectile motion with objects thrown horizontally and projectile motion with objects thrown at an angle. Okay, so once again, I've nicked one of Freya's tennis balls here, and she's at daycare today, so she's not going to be leaping in after her tennis ball, which she does do in some later videos. All right, so ladies and gentlemen, enjoy the pun or the comic Foxtrot, always good, and this one's very appropriate. Okay, so ladies and gentlemen, let us begin. Okay. So what we have here is we are going to be looking at when objects are thrown into the air or launched into the air by some means or another. When it's thrown into the air, it's called a projectile. Any single object in free fall is considered a projectile. So we have three scenarios. Number one. You take an object and you throw it vertically. This is the simplest of the scenarios. Like that. Just up and down. Hitting tennis balls on the Chromebook. Okay. There you go. That's it. We've already done that in the section titled Free Fall, which was right before your last quiz. Now, these are the ones we are going to be doing today. In the first video, we're going to be looking at this guy. In the second video, we're going to be looking at this guy. So we're going to start today's video. We're going to be doing objects thrown horizontally. Sorry about the background noise. My uncle and my husband are finishing the basement, so you can hear power drills and what have you. They're doing drywall today. So you have your tennis ball, and we're going to throw it. So notice when I throw this ball, it goes horizontally. Okay, that's the type of motion that we are looking at. Okay, next video, we're going to be doing objects thrown up and over like that. Okay? Okay. So, ladies and gentlemen, objects thrown horizontally. This is our focus for today's video. All right. So, these guys, like our 2D vectors, these guys both are going to have a vertical and a horizontal component. Now, we're going to be having to approach these a little bit differently than we did in the previous lesson, because our motion is now going to be different. We have, on our one hand, we're going to have accelerated motion, and on the other, we are going to have uniform motion. So we need to keep our vertical and our horizontal math completely separate. Okay? So these two components must be handled separately. Okay? The two components, so the horizontal movement and the vertical, are independent, which means they don't impact each other. The only thing that is allowed to be in both sides of the math is time. I want you guys to put a big star beside this. I want you to circle this. I want you to emphasize its significance. Because time is going to be our linking factor between our vertical and horizontal. So here, notice when I throw the ball horizontally, on the horizontal, it's uniform, okay? It is uniform motion on the horizontal. So that means anything to do with horizontal motion, you must use this equation. That is the equation in which you're going to use for your horizontal math. Nothing else, and only on the horizontal. The vertical motion that vertical portion, when we throw a ball horizontally, well, notice the ball is still accelerating downwards. It's moving this way as well as this way, so that's why we get that curve. Okay? Now, when an object is thrown horizontally, now this is horizontal only, our VI on the vertical is going to be 0 because it has no vertical velocity at the very instant it's released. Notice I'm not throwing it up or down. I'm just throwing it sideways. Okay? So the moment I let go of this, all of the velocity is going this way. Okay? There is nothing up and down yet, until it gets accelerating. So that is important. And your acceleration in any projectile motion question is going to be your gravitational acceleration of 9.81 meters per second squared, and your direction is going to be down. Now, so you could choose to make it positive or negative depending on the scenario. Now, your equations that you're going to use are going to be any of the 5 acceleration equations. So you guys see these 5 equations that we've highlighted in pink in previous videos? Those are your 5 acceleration equations. Those are the only ones that you're allowed to use on the vertical, because the vertical accelerates, okay? So let's write this down. You can use any one of the 5 acceleration equations, okay? And remember, depending on what values you have will depend on which one you use. So your VF, your VI, T, A, D. Okay? So any one of those 5. You pick the one you need based on the scenario, but vertical, acceleration, horizontal, uniform. You must know that. Less than subtle hint. All right. So before we start our 2 practice problems on this topic, we are going to draw some vectors. Okay, so let's start with red. Our red arrow is going to represent your vertical velocity. Your blue arrow is going to represent your, I got vertical and horizontal again, backwards. It's Monday. Red is horizontal, blue is vertical velocity. Okay, so ladies and gentlemen, let's start with the horizontal velocity vectors. This is the easier one. Why am I saying that this one is easier? Because it's uniform. The horizontal velocity, as this cannon is firing this cannonball off the cliff, it's going straight. So that means its horizontal velocity is going to be the same. So you should be drawing these arrows as close to the same size as you can. Your horizontal velocity is uniform. So that means it's going to be constant. However, Vy is accelerating. At this point, you have no Vy. It's just released from the cannon. Okay. However, as that begins to fall, because it's accelerating, your Vy is going to be increasing. I'm going to draw that arrow a little bit bigger so it's a bit more obvious. Okay? Because when you accelerate, your velocity is going to increase or decrease as time goes on. In this case, our velocity is increasing, so you need to have bigger and bigger arrows. Well, let's pretend I'm going to have this pale blue here. This is going to be my acceleration on the y. Now, what is acceleration in this case? Gravity. So it's 9.81 meters per second squared, and it's going down. So if we're going to draw our acceleration arrows on this, they're all going to be the same size because the acceleration is not changing. The velocity is changing. It's going faster downwards. But acceleration is constant at 9.81 meters per second squared down. All right, guys? Okay. So there are your vector arrows. Let us look at how to do these these calculations. Once again, I know I harped on this in the last question, and I'm going to harp on it again. Organize your page properly. Because these questions are big. These are going to take up the whole page again. Especially when we get into our non-horizontally thrown projectiles, those are definitely taking up a full page. If you don't organize your page, you are going to have a huge mess. And if you make a teeny little mistake, and you hand me in a disaster that I can't follow, I can't give you the full point because I won't be able to find what you did wrong. So organize your page, make it neat, and how you organize your page here makes a difference into whether you're going to get this question right or not. So pay attention to how I organize my page as well. Okay? Okay. All right. So, ladies and gentlemen, an object is thrown horizontally. That is your key word right there. That is going to tell you a whole bunch of information. With a velocity of 20 meters per second from the top of a building, 50 meters tall. How far from the base of the building did the object hit the ground? All right. Well, this is a bit of a mess as far as we've got two heights and we've got two distances. We've got height and distance and speed and time. Ooh, so much stuff. Let's draw it. Drawing is a very valuable way to help you visualize. Humans are very visual species. And when you look at how much of our brain is dedicated to vision, we'll talk about this in Bio 30. But you have a whole chunk of your brain back here called your occipital lobe dedicated to vision. Tons of space in the brain is dedicated to it. It's our most predominant sense as a species. So being able to draw something and to see it, and as you're drawing it, you're using this part of your brain up here, the parietal lobe, and you're able to process and think about it without having to look at these numbers and go, what do they mean? So I know it sounds silly, but draw it. If you're ever unclear of what's happening in physics, just draw the scenario. And I am no artist. Like, I've taught art before, and it was a disaster for everybody. Thank goodness it was like grade 6 art, but even so, it was bad. So here's the ground. Here's the building. Okay. So, like, once again, we're not talking fine art here. Here's the ball. Okay. It is being thrown horizontally with a Vx of 20 meters per second. Okay. It is being thrown from a height of 50 meters. You have been asked to find how far from the base it goes. Okay. And the dotted line is going to be its trajectory. Okay. All right. And remember, thrown horizontally, what does that tell you? Your VI on the Y is going to be 0. Okay. Look at what we have now, guys. We now have something to think about. This shows us our scenario a lot nicer than just the numbers type scenario. Okay. Your next step, ladies and gentlemen, is to break everything into horizontal and vertical components. Okay. So you're going to show your work in this manner. If you do not organize your work into horizontal and vertical components in some fashion or another and label it, your work is going to be a mess. You are not going to be able to find out where stuff is. I'm going to have a harder time marking it. And if you make a little mistake, I won't be able to find it. So organize your work. All right. So it doesn't matter which side you put on which. I'm going to write vertical here. Okay, so that's my y. And then I'm going to write horizontal here. This is where writing out your work and showing what you have is even more important than in the small questions. If you don't list out what you have here, you're not going to know which numbers are going where, and you're going to get them all blended and mixed up. List out what you have. Okay. This particular topic, projectile motion, is probably one of the more difficult of the unit. And it is blending most things, like everything we've done before this is leading up to this point. So list out what you have, show your work. It's a lot of stuff to keep track of. Okay. So let's look at the information that we have available. On the vertical, we have 50 meters. Well, that's on the vertical. Well, that's height, but remember, height is distance. So we know we have a distance of 50 meters, or a vertical displacement of 50 meters down. So because I have labeled things vertical and horizontal, I don't need to label y's beside all of my letters, but you can if you want to. So dy under the vertical. And okay, horizontal velocity. Okay, so that means my Vx is going to be 20 meters per second. This is my x. Now, something else you could always write down here is vertical. Remember, vertical is accelerated motion, and horizontal is uniform motion. So that's going to change what information we have available and what we're going to use here. Okay, well, our question mark here, we've asked to calculate how far from the base of the building. Well, that's our horizontal. So that is going to be our distance or displacement on the x. Okay, so that's what we're trying to find. Now, what else do we have? Well, remember, because it's thrown horizontally, that means our VI on the y is going to be 0 meters per second. What is the other piece of information that we have that is implied here? Acceleration. What is the acceleration of an object that's dropped? 9.81. Okay. So ladies and gentlemen, we need to think about our direction. I am going to choose to make, what do I want to do? I'm going to make my acceleration here positive because I have only one vertical direction in this question. It's down. Okay. I do not have motion that's going up and down. I don't have opposing motion in this case. So I'm just going to choose consciously to make down positive and up negative. Okay. Okay. Well, we now have everything at this point that has been given to us. We've organized our page really nice and neat, and we can see clearly what it is we have available. Well, we're missing some stuff. Let's look at our horizontal piece here. Well, we need to find distance. We have to, it's uniform motion, so we have to use V equals d over t. What are we missing? Time! How can I get time? Well, not on the horizontal. I don't have enough info. I have to get time on the vertical. Remember, ladies and gentlemen, what we mentioned earlier? This piece in your notes, this guy here, I told you like to put big stars around time. Time is the only component that can jump between the x and the y. So we need to calculate time. Your first mission with any projectile motion question, your first goal is to get time. Okay? So by finding time and getting time, you can then jump from one to the other. So I am going to calculate time on the vertical because I absolutely can do so. Well, I need to pick an equation. I have d, vi, a, and I'm looking for t. Well, the equation that is going to work off of your data sheet is this guy. Well, v VI is 0. Now I want you to look at this question here. Notice there's time in 2 places. So you can solve this with calculus, which you haven't taken calculus yet, unless you're in grade 12 taking this after you've taken calculus, but that's going to be the minority of you guys. But this, VI is 0. 0 times time is 0. So we are left with D equals 1/2 AT squared. That's better. Now we can solve for time. You are not ever going to have to solve for T in this equation unless the VI is 0. So then that way it cancels out like that. So you don't have to worry about finding T in 2 places like that. Okay. So, ladies and gentlemen, now we can rearrange this. So what I'm going to do is I need to get T on its own. So I'm going to multiply by 2 to get rid of that half, or you can divide by half, I don't care. And then I am going to divide by A to get rid of them. And I'm going to do that on both sides. Multiply by 2 and divide by A. So my T squared is going to equal 2D divided by A. Well, now I need to square root to get rid of that T. So T is going to equal 2D divided by A. Whoopsie. And square root the lot. I have to scroll down here. There we go. I am now going to put my numbers into my equation. So I've got 2 times 50 divided by 9.81, square root the lot. And you are very, very consciously and carefully going to put this in your calculator in the following fashion. 2 times 50 equals 100. Divide 100 by 9.81. Enter. Second square root, second answer. That's the order you put it in your calculator. Okay? So once you do that, you're going to wind up with the lovely number for your time of 3.1927 ... seconds. Okay. Well, now we have time. We got time for this question. Get it? So you're going to take this time and you're going to bring it up here. Okay? Time is the only thing that can jump from one side to the next. Okay? So that means our time here is 3.1927 ... seconds. Well, guess what? We now have all components on the horizontal to find the distance. So V equals D over T. I can rearrange this. D is going to equal V times T. And then I'm going to multiply my values together. All digits, no rounding until the end. Okay, so ladies and gentlemen, once you plonk that into your calculator, you're going to wind up with 63. That's a 3. That's a really messy 3. There we go. 63.855 ... So, sig digs, units. Now, do I want direction here? No. I said how far. Okay. How far means distance. How far is scalar? Okay. So I don't want direction here. So what this means is I need, let's go back up and look at the question to confirm my sig digs because I forget how many. Okay, there's 3 here and 3 here and 9.81 is 3. Remember, ladies and gentlemen, an implied 0 is not sig digs. Okay, so a VI of no VI, unless I said 0.00, but I didn't. I implied it. So that means you do not count it toward your sig digs. Okay, because at rest is nothing. There are no sig digs with the words at rest. Okay, so that means 3 sig digs. And I'm going to look for my rounding. So 1, 2, 3 sig digs. I then go look at the 4th and the 5th. Well, these 5s are going to round up that 8, 2, and 9. So 63.9 meters. Sounds good, guys? Okay. All right, so that is horizontal velocity. We're going to do one more, or horizontal projectile motion. We're going to do one more, and then you guys are going to go do some practice problems. Alrighty-o? Alrighty-o. Okay, so an airplane is moving horizontally with a constant velocity of 115 meters per second when it releases a care package that falls to the ground. Now remember, this care package is going to have the same horizontal velocity, initial velocity, as the airplane when it drops. If the care package lands in a village directly 1.72 kilometers horizontally from the point it is released, what is the height of the plane when the care package is dropped? Whew. It's a lot. Once again, that's a lot of stuff. There's numbers and distance and details and villages and airplanes and So take a deep breath and draw it. So I am going to draw an airplane. I'm going to draw a box and call it an airplane because, I can't draw an airplane. I'm using that Wacom writing tablet thing to write on the screen, and it's hard to draw on. So this box is my airplane. There we go. Fine art indeed. Now we have a care package. There's the care package. It is dropped from the airplane. You have been asked, what is the height of the airplane? Okay, so there's the ground. Okay. The airplane is going this way. That means the care package is also going this way with a Vx. This is Vx. It's on the horizontal of your 115 meters per second. Okay. Well, the village, this is not to scale, guys. There's our village. It is a horizontal distance of 1.72 kilometers. Oops. All right. Which, if you want, you can convert to meters right now. Okay. Oops. I accidentally wrote 1 too many zeros. Beg pardon. Okay. So, now, ladies and gentlemen, we have our distance there. Okay, well, what is the VI on the Y as the care package is falling like this? 0. VI on the Y is going to be 0. What is your acceleration? 9.81 meters per second squared. And that's acceleration on the Y. Okay. We've now got kind of a visual to see what we're dealing with here. So much, much easier to understand. So when in doubt, draw the scenario. Okay, take your time about it. Understand what these numbers mean. Like the half the battle with physics is understanding what the numbers mean and what you got to do with them. Once you have all that figured out, the actual calculations are the easy part of this. Okay. The hardest part is trying to get each piece sorted to where it needs to be. All right, so remember, you need to organize your work into your vertical and horizontal. I'm going to I'm going to label this here for you. My vertical, which is Y, is accelerated. X, which is your horizontal, this is uniform. Okay. So by organizing your page into the 2 columns, vertical, horizontal, your life is going to be infinitely easier. Okay. Okay. So now we're going to list out all the values we have, and we're going to sort them into vertical and horizontal components. Okay, well, my Vx is 115 meters per second. It's uniform, so I only have one V. Okay. And, all right, well, my VIY here, so my VIY, that's implied to be 0. Okay, my acceleration on the Y, now it's down, so that means you need to consciously think about its direction here. Because I only have one Y component, everything's going down, so that means I'm going to choose down, actively choose down to be positive. And then, what else do I have? Well, I have my horizontal distance here, which I've already converted into meters. All right. So, ladies and gentlemen, let us now have a look and see what we got to do. Okay. I need to find the height that this is traveling. Well, on the vertical, I only have two variables. I've got my VIY and my acceleration on the Y. That's all I've got. So I need to find the dy. Well, I need three variables to find the fourth. But look over here on the horizontal, guys. I have time over here, and I have two of the three that I need, because remember, horizontal's uniform. So I can find time over here and then bring time over here, because time is the only thing that is good in both places. Okay, so V equals D over T. I'm going to rearrange this, so T is equal to D over V. And then I'm going to put my numbers into the appropriate places. And plonk them into my equation. I'm going to calculate the time. And that's going to be 14.9565 seconds. What do I do with that time? Move it over. Unless you're going to put it in a stew. Thyme is a great herb in chicken stew. So good. Delicious. Okay. So I'm going to move my time over here. We're going to time travel. Yeah. So make my 14.9565 seconds. Well, there we go. That's a little better. I've got D, A, V, I, and T. Will you look at that? Same equation as last time. VI is 0. VI times time. So 0 times time is going to give me 0. That's going to cancel. So I am left with 1/2 AT squared. I'm going to rearrange this to isolate for what? Well, I actually don't have to rearrange. I'm just going to use this because I'm trying to find dy. So 1/2 times 9.81 times the whole number from your calculator. Bring the whole thing in there. Do not round. At this point, 14.9565, square that. Once you've put this properly in your calculator, you are going to wind up with 10972.2 meters. Now we need sig digs. Let's go back up to the original question and look for our sig digs. Well, I've got 3 here and 3 there. 9.81 is 3, so I have 3 sig digs. Now, I have been asked for the height of the plane. Okay, I have not been asked for the vertical displacement. So that means I've asked for another scalar quantity. So that means I do not want a direction with this. I want 3 sig digs. I'm going to have to put this in scientific notation. 1, 2, 3, 4, because my whole number's got 4. So I'm going to look 1, 2, 3. I'm then going to look at this. Well, this 7 is going to round up. It's going to bump that 9. That 9 is going to bump that 0. Okay? So 1.10 times 10 to the power of 3. 1, 2, 3 meters. Okay. Or if you want, you can convert it back to kilometers and go 1.10 kilometers. I'm okay with either. They both mean the same thing. But this is why it's important for you guys to show the units that you need. Okay, so a classic example of why using your units is so important. There's a case of, I remember what airplane it was. It was a Canadian airplane, or it was a flight in Canada. And this airplane was flying from one part of Canada to another. I can't remember which one. And because the fuel gauge that was being used to add fuel into the airplane to determine how much was being added was in liters, and the plane, being American built, said it needed so many gallons of fuel. So between gallons and liters, and as you guys know, there's about 4 liters in a gallon. It's like a big jug of milk. That's 4 liters. That's a gallon of milk. So they added in like a quarter of the fuel needed, and the airplane ran out of fuel midair, and they had to make an emergency landing. Everyone survived, thank goodness. But yes, that airplane ran out of fuel midair because someone forgot to convert or check their units. So don't be that guy and check your units. Sounds good, guys? Cool beans. Alrighty-o. So, ladies and gentlemen, here are your practice problems. Those are from your workbook. I want you guys to do these practice problems, do at least a couple of them. Get really comfortable with this before you do your assignment question on this, and before you guys do your go on to the next lesson. It's really important because the next lesson, or the next part of this lesson, the next video, is going to be harder. We're adding more components. You're so excited. I'm excited. So, ladies and gentlemen, do your practice problems. Make sure you're comfortable with this before you go on to the next one. Sounds good? All right. So, ladies and gentlemen, no fires, injuries, or explosions. And see you in the next video.